When we look at a mountain range or an ocean basin, it is easy to assume the rock is simply the stage. We tend to view the Earth as a massive, permanent physical structure, and life as a fragile passenger sitting on top of it. If you want to see what a planet looks like when it is dictated entirely by physics and static geology, look here. This is Mars, a world where the internal heat has largely faded, leaving a barren surface. Billions of years ago, Mars held streams, muds, and the chemical building blocks required for life. The divergence between our two worlds raises a difficult question. Why did one become a frozen desert, while the other remained a dynamic chemical engine? Part of the distinction lies in the behavior of life itself. On Earth, biology acts as an aggressive physical force. It forces its way into solid rock, splits crusts apart, and alters the very chemistry of the atmosphere. Geologists study this intersection through geobiology, which maps what is known as the Earth system. It recognizes that biology and geology aren't separate. They are locked in a cycle where even the hardest rocks are modified by the softest organisms. To understand how biology shapes rock, we have to rethink the biosphere. The vast majority of it consists of nearly invisible microorganisms, and those organisms occupy an immense volume. This biological layer extends from several kilometers up into the atmosphere, straight down deep into the solid subterranean rock of the upper crust. All of that accumulated biomass operates as a single thermodynamic system. It continuously pulls in solar radiation, water, and raw nutrients to function and grow. Because of its sheer scale and constant metabolic processing, this layer wields enough energy to function as a planet-altering geologic force. How exactly does soft tissue break down solid mountain ranges? Geologists call this process biological watering. Organisms hunt for nutrients trapped inside stone. To get them, plants and microbes excrete highly corrosive chemicals, actively dissolving the rigid lattice of solid minerals. Over thousands of years, this continuous microscopic chemical attack grinds away at the surface. It strips down massive peaks and turns them into loose sediment and soil. Even the oxygen we breathe plays a part. Generated directly by biological photosynthesis, atmospheric oxygen acts as a corrosive agent that alters the chemistry of the planet's rocky crust. Life also actively builds entirely new geology. Geobiologists track this construction by mapping biogeochemical cycles, specifically the movement of carbon. Look at the surface waters. Plankton and larger marine life pull dissolved carbon dioxide from seawater to construct hard shells. When they die, their carbon-rich remains drop out of the biological zone, sinking through the twilight layer to the sea floor. Over millions of years, the crushing weight of the ocean compresses that dead biology into solid lithosphere. It creates massive limestone formations and thick seams of coal, like the terraced walls you see here. Today, modern industry digs up those compressed organic remains and burns them, forcing that trapped carbon right back into the atmosphere. This indicates that large portions of the ocean floor and our global fossil fuel reserves are essentially massive geological structures built out of the remains of ancient life. This creates a reciprocal feedback loop. While the biosphere influences the composition of the rock, tectonic geology dictates the survival of the life. Earth's internal heat drives plate tectonics. This creates volcanoes that rip open the crust to resupply the atmosphere and oceans with trapped water and gases from the planet's deep interior. As these tectonic plates collide, they thrust up massive mountain ranges, forging entirely new surface topographies and distinct climate zones. Ecosystems are forced to cross these new physical barriers and adapt to changing weather patterns, driving biological evolution. The Earth system operates as a continuous negotiation between internal geologic heat, external solar radiation, and the biological engine. This interplay is why Earth survived while Mars froze. Our planet relies on a specific balance: active tectonic plates churning below, and a relentless biological layer circulating chemicals above to keep the system reactive. It is impossible to divide this planet into the living and the non-living. A mountain peak, a breath of air, and a microscopic cell are all integrated components of a single, massive living engine.